Hey everyone, and welcome back to the channel. We're going to be mixing things up a little bit today by doing some Linux administration content. And more specifically, we're going to be going over a lab that I wrote that accompanied a webcast that I gave a week or so back about Linux file permissions. I wanted to give some time between the release of the lab and this walkthrough so people could kind of explore it on their own, but I did want to do a walkthrough just so that I can kind of show how I thought about the lab and how I would go about solving some of the challenges. Something that's interesting about this, as I mentioned in the webcast, is that this lab is actually kind of a sneak peek of some labs that will be available for my Linux fundamentals class that I'm currently building. And I don't have a lot of details about that right now. It's a ways off from being released, but it will be a pay what you can class. And I'm hoping in the next like 6 months or so. I'll talk a little bit more about it like later on in the video, but I just wanted to give everybody a heads up. So if you didn't get a chance to see the webcast, I recommend watching it. It's basically the lecture to go along with this lab. I will cover some of the lecture as I explain the lab challenges and complete the lab challenges, but if you're interested in watching the webcast, the link will be down in the video description. So the first thing we need to do to be able to run this lab is we'll need to download it and get it operational. And so I have it hosted on my GitLab page. The link is down below in the video description, so feel free to give that a click and follow along with me. If we look at the README, it's going to tell us that we need Docker to run this lab. If you've got a Debian or Ubuntu machine, then you can follow along with me. If you're running CentOS or Fedora, just quickly Google how to install Docker if you don't have it already. If you don't have any virtualization, like you don't have VirtualBox or VMware or anything like that, there are plenty of guides out there on how to install Ubuntu on WSL. So that's Windows Subsystem for Linux. So you can actually run a Linux system in your Windows system. So it'll work just fine there. That's actually how I wrote the lab, was from a Windows system. Or if you're running OS X, it's pretty easy to install Docker on Mac. So you can check that out. And this lab should work just fine on an M1 Mac. Don't worry too much about that. What we're going to do on the Ubuntu or Debian side is we're going to use apt to install Docker. And the package name is docker.io. If you just run apt install docker, you'll get something else, and that's not going to work for you. So you want to do docker.io. And we're going to hit enter. We'll type in our password for sudo. And we'll say yes, and this will just take a minute to install. Okay, now that we've got Docker, we're going to have to do a little bit of permission surgery to be able to run Docker from our user. So if we run like a Docker container, or a Docker command, so we run like Docker container ls, it's going to yell at us that we don't have permission to hit the Docker socket. So the way we can solve that is we'll use a tool called user mod to modify this user. We're going to do -a for appending. So we're going to append new groups. Capital G will allow us to add group names. And we're going to add the Docker group. We're going to add our user to the Docker group. So in this case, I'm logged in as Rook. There's my user right there. So I'm going to add the user Rook to the Docker group. We're going to make sure you put that A there because it's going to append the Docker group rather than just replace all of your group memberships with Docker. You do not want to do that. That'll mess up your system pretty bad. We're going to run that. And if we run ID, we don't actually see Docker there. And the reason for that is that the group membership is determined at the session start. So since we're still in the same session, it hasn't reloaded our group memberships. So one thing you can do is you can log out and log back in or reboot your system or any of that stuff, which is fine, I guess, but we're just going to start a new session within our current session. And all we're going to do is use the su switch user command. We'll add the dash there to basically start a new login session. And we're going to specify that we're going to su to our own user. If you don't put your username there, you're going to su to root, which is the default for su. We don't want to do that. Put in our password, and we're in a new session. It looks identical, but if we run ID now, we see that we're in the Docker group. So then we've got Docker running. We should be able to run like Docker container ls, which we can. No containers are running. Totally fine. We just started. But now we're able to run these without an error, which is great. So let's flip back to the guide. And we can see here from the guide, if you read it, you'll see that there are two different ways you can run this lab. The first one is to clone the repository and use the start lab and stop lab scripts. You don't have to do it this way. This is just the way the class does it, and it's for workflow reasons for the class. So they're here for this lab, even though it's not technically part of the class yet. I'll show you how to do this in a second. You can also just directly run the Docker commands. So we'll do that now. If we take this first command, it's going to look for the image that I've created. It's not going to find it locally, so it's going to go out to this repository and download it, and then it'll run it using -D for daemon mode, which means that it's going to run in the background. It's going to set the host name and the container name to Linux Fun 14, and that just is the Linux fundamentals class, and this is part of module 14 of that class. So we're going to paste that in there, and when we run it, it's going to not find it locally, so it needs to download the image. So that's just going to take a minute or two, depending on your internet. I think it's almost done for me, but we'll just wait for this to finish. All right, now that that's finished, I've got that image downloaded and I've got that container running locally. So if we run the docker ls or container ls command, we'll see that we actually have an image running, and we can see that the name of it, it's a little funky because I have the text enlarged for this terminal, but we see that the name is that Linux Fun 14. So if we look back at our instructions, there's another command that allows us to exec into or execute into the container. And all this is saying is that it's going to set the lab files as our working directory. We're going to exec in as the user student, and we're going to exec into the Linux Fun 14 container, and we're going to execute the bin bash command. So we're going to exec in a bash shell. But if we paste this into our terminal and hit enter, now we are inside of the container, and we can see that we are the user student on the Linux Fun 14 container in the lab files directory. And so that's the way that we would get in using the raw Docker setup. Here you can see that I've reverted to an earlier snapshot, and I'm going to walk through how we do the git clone method and using the start and stop lab scripts. So if you don't already have Git, we're going to have to install it. We're going to do the same thing we did before with Docker. We're going to sudo apt install Git. You can see that I already have it. If you didn't, then you could run yum install Git or apt install Git, whatever you need. But I already have it. Generally, I like to segment all of my Git repositories into a separate directory instead of just having them in my home directory. So I'm going to make dir git, and I'll cd into that directory. Then I need to git clone this repository. So if we scroll up to the top, we'll see this clone button right here. And we can use the clone with HTTPS link. So we'll just go ahead and click this little button to copy the URL. Go back here and we'll git clone, and then we'll paste in that URL. So all that's going to do is it's going to pull down all of the files that's in this repository. And once it's done, if we run ls, we'll see that we have a directory named what the repository directory is. So we can go in there. If we run ls, we see that there's a start lab and a stop lab, just like our instructions show us here. So we can clone the repository and use the start and stop lab scripts. The first time you run start lab, it's going to do the same thing that our Docker commands did in the previous example. So it's going to download and install that image the first time. Once you have done that one time, if you run start lab again down the road, you want to redo the lab later, it won't have to download it because it's already there. But we're going to run start lab. And the difference here is that once it's fully downloaded, it actually jumps directly into the container. Instead of having to download it and then exec into it in two different steps, that's what the script does. Since we're in this container already, we can move forward or we can exit, and then we've got the stop lab script as well. And this takes a second because it's spinning down all the anything that's running in the background. So if we run start lab again, it'll put us right back into the container without having to download anything. So if we take a look at the rest of the instructions, we'll see that when we first load into the lab, there will be a README file in the same directory that we load into. The first thing we do is run ls, and let's run cat to README file. Now you can pause it and read this out if you'd like, but basically the way this lab is structured is that it'll kind of hold your hand up front, describing exactly what needs to happen and exactly what's going on. And as we progress through the lab, it does less and less hand holding, more just telling you what needs to happen and letting you figure out how to do it. The first thing we want to do is inside of the challenge 1 directory, there's a whole bunch of files, but only one of them are we able to read. So if we go into challenge 1 and we run ls, there's 40 files here. Now we could, start with file 00, try and cat it. Okay, what about file 1? No, file 2. We could do this, but we'd have to do it 40 times and up to 40 times. And that's just not fun, not efficient. And it's not the purpose of this lab, right? We want to learn how to do things the correct way. So the first thing we're going to do is we're going to run ls-l so that we can see the permissions in list form of all the files. And we can see here that most of these files have blank permissions, which means nobody can read, write, and execute. But if we scroll down, we see that file 36 has the read permission set for the student user, the student group, and other users as well. So we can actually cat file 36, and we get our second challenge. So what this is saying is that another user, not the student user, needs to be able to read this file, but they can't. That other user is part of the dev group. Okay, so there's a user group on this machine called dev, and the dev group needs to be able to read this file. Now, this is a very common thing to happen on Linux systems where you've got, like a dev system or a QA system, or you've got multiple admins adminning the system. You don't want 5 different people all logging in as the same user. So in order to give them access to the same files, you can put them all in the same group and then assign permissions to that group. So in this case, we just need the dev group to be able to read this file. The group permissions are already set to read, so we don't have to change anything about the permissions. What we need to do is change the default group for this file. And so we can do that using the chown command, the change ownership command. The way chown works normally, or I think the way most people use it, is that they'll chown for a user. So we'll say, oh, we want the student user to own it, which it already does, but this is just an example. So we want the student user to own file 36. Or they may know that if you do student : and then dev, you can actually set the user and then the group for a file. But not everybody puts together that you can actually just omit the user altogether so that you're not changing the user. You don't have to re-specify student because student already owns it. You just put the : there and then the group name, and that'll change the ownership of the file, the group ownership of the file. So when we hit enter, we get a pop-up telling us what the next challenge is. If we wanted to look back at the permissions for file 36, we can see now that the group ownership has been changed to dev for developers instead of the student group here. So let's take a look at what challenge 3 is. What are we doing? For our next trick, there is a file in temp in a directory called /temp/challenge4 that we can't read yet, but we should be able to make it so that we can read it with the change mode or chmod command. So we can go into temp challenge4, and if we look, we see that the challenge4 file, so the file that's going to give us what challenge4's text, we can't read. So challenge 3 is to figure out how to be able to get to challenge 4. And if we look, we can see that we can write to chal 4, but we can't read challenge 4. Now this is interesting. This is a little quirk of Linux. Even though we own the file, if we don't have the read permission, we can't read the file. However, since we own the file, we are able to change the permissions of the file. That's just a default thing that you always have, even if you don't have write permissions. Change mode or the chmod command doesn't care about the permissions that you have, only that you are the owner of the file. So we can actually use chmod to give ourselves the read permission. This challenge text says feel free to use the symbolic notation. And what that means is, if you didn't watch the webcast, is there's two ways to use the chmod command. We can use symbolic notation or octal notation. Now you might have seen something like this, where you use 777 to give all permissions to everyone for a file. That's the octal notation. And I actually break down how to read octal notation a bit better in the webcast, and actually how to not just memorize what the numbers mean, but actually derive what the permissions means every time. So you don't have to rely on your memory. You can just figure it out every time. But this says to use symbolic notation, which I think is the easier way to use it. And so the way we do that is that we can use U for user, G for group, or O for other. In this case, we're the user and we want to be able to read it. So we're going to use U, and we're going to add the R permission, the read permission to challenge 4. So this is just adding the read permission. If we wanted to set it to read instead of keeping the write permission as well, we could do U equals R, but we're just adding the read permission. We don't want to stomp on the other permissions that are there. So when we run that, we now see that we can read the file. We also see a new file pop up, but we're not quite ready for chow 5 yet. So let's go ahead, now that we can read chow 4, let's read that file. Okay, so we can read it. We've confirmed that we're able to read it. And there's a user that can't access the file chow 5 in this directory. We don't want to add them to any extra groups. We don't want to change the group ownership or anything. So we need to make the file writable by others. Try using octal notation this time. So, it's on you. This is the honor system, but you're here to learn. So, try and keep with what the challenge is asking you to do. We're going to use octal notation to do the chmodding for the file chow 5. We only want to add write permissions. We want to keep all of the existing permissions the same. There's kind of a trick to this, a little gotcha for this challenge. So if we look up here, actually, let's just kind of clear everything out. If we look at the permissions for chow 5, the owner, so us, the student user, has read-write capability. The group has read capability and not write or execute. And other has read but not write or execute. So it wants us to keep all that the same, but add write permissions to other users. So not changing the group or anything, just changing this. Let's figure out how to do that. So we're going to chmod. We already know we're going to change mode or change permissions here. And then the octal notation, like I said, is the numbers. We're going to set the first number to 6. What that's referring to is, if you break it down into binary, there are 3 permission sets, which look like, if you look at it like this, it's either on or it's off. So you can do that. You could do that. You could, do it that way if you wanted. But if you read binary, or how to read binary, even the first 3 bits of binary, this is 1, this is a 2, and this is a 4. And these 3 bits match up to these 3 bits. So if, in this case, we have read is on, write is on, and execute is off. So we have read is on, write is on, and execute is off. This in binary, 110 in binary, equals 6 in decimal or octal. So the first set is going to be 6, and that's our owner set. The next bit set is what they're called, is read only. So it's going to be 1, 0, 0. So we've got a 1 in the read place, 0 in write, 0 in execute. And this number in octal or decimal is 4. So we put a 4 in the group set. Now the next bit set is also a 4, but we want to add write capabilities. Now we already know that the first set is write, so we could just do 646. But, if we wanted to reason this out, we know that read is set and nothing else is set. We want to add write, and that's 6. So that's a super abbreviated version of how you can kind of puzzle this out every time you see it. And we're setting those permissions to chow 5. Boom. Check chow 5 for the next step. So here it shows that the file was 0 bits long, so there was no contents. And if we look at shell5 now, there are 262 bytes of text. So if we cat channel5, we can see what the challenge text for challenge 5 is now. So a user's complaining that they are unable to create new files in temp challenge 5. They have write permissions, so don't know what's wrong. Can you fix it? Remember to preserve existing permissions or you may not be able to read the results. So let's back up. We can see inside of temp that there's a challenge 5 directory. So let's take a look at the permissions for challenge 5. You'll notice that I do a -d here. If you just do a -l, what you will get is the list of contents of challenge 5. You don't want the list of the contents of challenge 5. You actually want the permissions of the directory itself. So -d tells it, don't give me the contents of the directory, give me the directory itself. And we can see here that we have read, write, and execute, but the group does not. It has read and write. And so they don't understand why that's happening. A idiosyncrasy of the way that directories function inside of Linux is that in order to actually do anything inside of a directory, you need the execute bit. What the execute bit does for a directory is it allows you to set your working directory to that directory. If you don't have the execute bit, you can't set your working directory to that directory, and therefore you can't do anything inside of it. You can look into it, but you can't create new files or rename files or anything like that. I go into a little bit more of the weirdness of Linux directories in the webcast, so I do recommend checking that out. But for now, you know that, oh, we need the execute bit here. So we want to preserve the existing permissions. So we can do this one of two ways. We can do the octal notation again, and that will allow us, we'd have to specifically set that this should be 7, and then this should be 7, and these folks should be 0, or maybe it's 1. But since they don't have read or write permissions, the execute bit's not going to do much at all. So we could chmod 770 for challenge 5 if we wanted. We could also add the execute bit for the group. So we could do g plus x if we wanted, and that's just adding the execute bit. If we were to equal x, then that would remove the read and write bit, and we don't want to do that. We could equal read, write, and execute, but I think the plus x is just fine for this. Excellent. So now we're supposed to look inside of the directory, and we're on to challenge 6. It's getting a little bit weird. A malicious user keeps changing the contents of /lab-files /.meta/lock-file. That file needs to read a certain value or else our automation goes haywire. We've checked the permissions. We can't figure out how they keep accessing it. Let's take a look at that file. If you're not familiar with how I'm copying and pasting with keyboard shortcuts, instead of Control-C and Control-V, it's Control-Shift-C and Control-Shift-V inside of like a Linux terminal. So we're going to LSL Control-Shift-V. Now, if we look at this, we see that the owner can read and write, the group can read and write, and everyone else, other, can only read. So this is a little confusing. The people who are supposed to read and write can. Everybody else not allowed to write. So how are they actually accessing this? If we like cat it, we can see that we've been pwned, right? This is bad. We don't want that. We don't want people who shouldn't be able to write to this file writing to it. Well, this is an extra functionality, an extended functionality of Linux called ACLs. This is another subject that I covered in the webcast. This little plus here shows us that there's some extended ACLs associated with the file. So we can use the get ACL command. Get file ACL command. So get facl, the get file ACL. And with that, we're going to look at this file again. And we can see that the user has read-write permissions. The user mal user has read-write permissions, and then group and other have read permissions only. There's this extra mal user that shouldn't be able to write to it, but they can because of these extra ACLs. Now, this is important. I think there's a lot of people out there operating in Linux today that have no idea that these exist. And if they saw that plus, they wouldn't even think about it because they just don't know to look for it. They don't know what it is. They'd see that the permissions are fine and move on scratching their heads. There's a companion command called set facl that we need to use to be able to remove that user. So if we take a look, we can remove an ACL specifically, or we can modify an ACL. Since we don't want this user to have any access, we can just remove that. So if we do a set facl, and we're going to use the X for remove, and we say user-maluser on the lab files meta lock file. Now we can see it like immediately, okay, now they don't have access. If we wanted to just double check that, we can run get facl again, and we see that there's no additional entries there. And we look here, there is a plus because extra ACLs have been created. They exist there, but the mal user isn't there anymore. This plus is just a clue to say, hey, extended ACLs for this file exist. Whether they're malicious or not, it doesn't give us that information. Okay, final challenge. Somewhere in user local challenge, there is a set UID script. We need to find that command. We should use the find command to find it. Okay, so I do go over the find command and some interesting bits about the find command, how to use it, cool little tricks with it in that webcast. But let's talk about set UID for a second. So there are additional permissions for files in Linux, and one of them is set UID. And what that means is for a script or a binary or some executable file, if set UID is set, then it doesn't matter who executes that command. It will run with the permissions of the owner of that file. If there's something that's set UID and the owner is root, but other can execute it, then anyone can execute that command with the permissions that root has. Now, there's a very good example of this that you may not be aware of, and that's the password command, the command you use to change your password on a Linux system. Technically, to change your password, you need root permissions because the password is stored in hash form in the etc shadow file, and that file is only writable and readable by the root user. You need to have root permissions to be able to modify the etc shadow file, and you're not a root user most of the time. So if we look at user bin password, we can see that there's an S here in the execute bit, and that's short for SUID. And we can see here that it's in red. That's kind of a colorized clue that it's set UID. That S is something special. Now, we talked about how 70 equals 111. So where is that S coming from? Because the ones are already full. Well, in addition to the 777, there's actually like a secret extra bit set there that is usually left off because you don't operate with set UID or set GID or sticky bits very often, but it's there. So 777 is actually the same thing as 0777. The important thing to know for this challenge is that the sticky bit is 4. If we look at these permissions, we would have what would be a 7 in this place. We have read and execute, which would be 5. And we have read and execute again for others. So that's 755. But to make it set UID, we're going to put a 4 in that extra 4th bit set. It's actually 4775. Scroll up a little bit. We're going to see that we're going to be looking in the user local challenge directory. So we're going to use the find command, and you could start in the root if you wanted, but the second argument in find is where you're doing the searching, and we already know that it's going to be inside of this directory. And the next thing we do is going to be our search directive. So you could do something like name is a very common one, or what I use more is iname for case insensitive. We could like search for like file 30, and we'll see all the different file 30s here. But we're not doing name, what we can actually do is we can do perm. And so what dash perm does, it's going to search for all of the permissions. And then after that, we'll do dash perm dash 4000 because we want to find any files inside of this with the 4000 permission bit set. Now we do a dash 4000 because we're just looking for files that have the 4000 set. If we didn't have the dash, then it would look specifically for files with the permissions of 4000. So if we run this, we get nothing. If we put a dash in front of it, it doesn't care what the rest of the permissions are. It just wants to know if that 4-bit is set somewhere. So if we run this, we see that there is a runme file inside of this directory. And if we run ls on it, we can see that it also has the setuid set. So if we run it like it asks us to, we can see that we finished. So congratulations if you made it this far. Thanks so much for hanging out with me, and hopefully you learned something. Hopefully you had fun running through this. Please reach out to me and let me know what you thought, and keep an eye out for the class. If you like this video, you may be interested in one of my other lab walkthrough videos, or maybe check out my CTF walkthroughs playlist.